Okay, hello everybody. Welcome to the first lecture of course Introduction to the Theory of Open Quantum Systems. So let me begin with some organizational remarks. So let me see what I have in my notes. Okay, so nominally this lecture, this course is about theory of open systems. However, the program of the course doesn't follow the typical courses or textbooks. Okay, so for example, maybe you heard about, maybe you even read it. Like the standard textbook is a Breuer Petrushkone, this guy, right? What we will be doing is something completely different than what's done here. Okay, we will be using some local brew here. Okay, some, let's say, modern approach, much more modern approach than typically. So that's first word of warning. Okay. Yeah, although the approach is different, is more novel, but still it's not like we will ignore those standard textbook stuff. We will get to them eventually, but it will be in very unorthodox order. Okay, but so this is the first word of caution. Next thing, okay, so my intention with this course is to let's say to give you a fishing rod rather than fishes. Okay, so what I mean by that is that I want to teach you and give you like the theoretical tools of like general purpose theoretical tools. Okay, rather than, let's say, focusing on Dzień dobry. Rather than focusing on some examples, I want to talk in a more more abstract level. Okay, so it's like my intention is to give you enough knowledge, enough know-how that when it comes to applications, you will be able to just take this abstract theory and apply it, and to have enough confidence to mold it into a way that fits your purpose. Okay, so rather than talking about examples, we'll be talking on abstract stuff, abstract theory. And the reasons, I have like two reasons for this choice. One is I just despise the approach where you just show examples. I just don't think it works. I don't like it personally. So this is a matter of opinion. But the other stuff is more important. The other reason, it's like if you open systems. If you think about it, any system interacting with any other system is formally an open system, right? So this is like the theory of open systems deals with everything. Okay, it's a theory about everything, although not theory of everything. Okay, so it's very broad, right? In its conception is very broad. So if you talk about you focus on some couple of examples, typically those that can be solved exactly, right? Then you run into this risk that you will make this false impression that those couple of examples are like representative cases. Okay, that open systems are like those couple of examples we just solved, and that's just this is risky, right? And it's not true typically. There are a couple of examples where you can like solve stuff analytically, and they are, as usual, very special. Okay, so it's like building all your intuitions on that. It's just asking for trouble, right? That's why we want to stay on more abstract level here. So that's it. Okay, and as a result of that, this course will be kind of technical. Okay, there will be a lot of technical stuff here. So it might be a little bit maybe difficult to digest. So I will do my best to, to keep the difficulty level climbing, not very steeply. I will try to sound any difficulty spikes and stuff like that, make it palpable, try to explain everything as best as I can. However, it's still technical, so there is no better way to absorb technical stuff as by doing, right? Doing the technical stuff yourself. Hence, there are assignments to our course. So in each lecture, there will be a bunch of home assignments that I will ask you, recommend you to look at them at home, okay? And the way I'm thinking about them is like, they are kind of, to help you out with absorbing the technical material that was given in the lecture, but also it's some kind of a supplementary material as well. For example, some proofs, I won't waste time on talking about proofs. The assignment will be, do the proof yourself. And the way I imagine it to work is like you take the assignment, you look at it, give it a think, maybe give it a try to solve it, but afterwards consult the solution, because for every assignment there is a solution. So I should I should show you the reading materials. Where is my right? So if we are not basing this on any textbook, but there are reading materials. So if you visit our division website, okay, you go to teaching, and you open the page of this course. You see here are materials. Okay, so there is this lecture notes. It has the first edition was published in 23rd. Okay, but since then a lot of I plan to improve it. So there is an ongoing work in progress. The second edition, and this is the reading material for you. I will be going through this as very closely to what's written down here. And the assignments, and I talk about the assignments. So you see, you will have those assignments in the text, and you can click solution, and there is a explanation, okay? So the assignments is, you look at them, try to solve them, or think about them, how you would approach it, and then check out the solution, and you try to absorb what's going on. Okay, and I hope this will help you to catch up if you get lost somewhere on the way, or some additional info will be there, some additional tricks and methods maybe to learn and use later and stuff like that. Okay, they want to talk about what else? All right, so the last thing, the program, I guess, so the outline of the course. So it will be basically 3 chapters. We'll start by talking about dynamics in closed systems. So standard Schrödinger equation, basically, just to make sure everyone is on the same page. If you had some quantum mechanics previously, you might think it will be boring, but there is a twist. In each chapter there will be something interesting, okay, of some general purpose interesting stuff, not only for this course. So first, closed system dynamics, then we'll go to stochastic dynamics. So this is kind of a weird thing, but it's something different than standard stuff. It's like a bridge between closed and open systems. And There will be some stuff that we will, some methods we will learn, some concepts we will learn on the example of stochastic dynamics, and then we go to the main event, the dynamics in open systems, where we will use the stuff we learned previously and apply it to the to this ultimate case that we are interested in. And afterwards, there are some stuff afterwards. Okay, we'll get there when we will get there. Okay, but this is like the main structure is was given here. So with this lengthy, boring introduction out of the way, I think we can start doing the even more boring stuff, or maybe it won't be so boring. So let's get to the technical stuff. So like it's written here, chapter 1, dynamics of closed systems, 1.1. So the titles are like in the reading material, okay, in the lecture. So you can identify where you are just by comparing. All right. So first, we'll talk about unitary evolution, Hamiltonian Schrödinger equation. So in the standard formulation of quantum mechanics, the one you were taught in your basic course on quantum mechanics, they tell us that when you have a closed, isolated system, closed means that it's the only quantum system in the universe. It doesn't interact with any other quantum system. Isolated, by isolated, I mean that there is also energy is conserved. So there are no like external fields poking the system and exchanging energy with it. So it's close and isolated, so it doesn't interact with any other quantum system or any other classical system. Okay, so it's completely isolated from everything. And this in standard formulation, they tell us to this system you can assign a state, time-dependent state, which is represented in the formalism with a ket state, which I will write as like this. So this is state at time t. Okay, so this is a vector, unit vector in a Hilbert space of the system. And this guy, it changes in time. And the way it changes in time is given by, so if we go from t to some t delta t, they tell us there is this transformation u, depends on the time interval, that takes this ket state at time t and pushes it forward in time to the later time, okay? And this guy, u, evolution operator, so evolution operator, so it's formally is a function of time, right, with values in operator space, and this guy is generated by the Hamiltonian. Hamiltonian H of the system. So H is Hermitian. So Hermitian means that when I do dagger on H, nothing changes, right? So it's Hermitian, and it's in standard formulation, and I think in any formulation of quantum mechanics, it's supposed to represent energy of the system, right? So if we are isolated from everything, it's constant. It's a constant operator because energy is fixed for our system. And it generates the evolution operator in the sense that UT operator is given by exponent minus IHT, which the symbol means that there is this series, it's defined by the series. To the power k, k factorial, hk, okay? This is what means that operator is generated by generator, okay? The nomenclature comes from, I think, theory, group theory. And I don't know if you've seen it before, but this is how I will be using the word. And there are a couple of important consequences coming from this definition. Consequences of definition star. Okay. So the first one is the famous Schrödinger equation. So state ket satisfies the famous Schrödinger equation. Schrödinger equation. Schrödinger equation, I'm sure you know how it looks like. So we take a derivative over t of psi t equals, let's write it like this, t psi s minus h u t minus s psi s, which equals minus I h psi t. Okay, so oh, sorry, t. Okay, now it's correct. So why this satisfies this? Okay, why does it satisfy this equation? That's hopefully it's kind of obvious here. If you differentiate evolution operator, right? It's you go into the you can use this series representation. You go with derivative under the sign of sum. The only thing that depends on time is the parameter here, and it's I mean that's why it's called exponent, right? Because derivative just takes down the exponent from the exp in front of it, right? So oh, and what else? Yeah, and as a matter of fact, you can treat Schrödinger equation as it's a valid definition of evolution operator, alternative definition, right? Rather than just saying that it's this exponent generated by h, you can say that here is a Schrödinger equation with initial init condition. If you give it in initial condition, let's say t at s equals psi s, then the solution, the unique solution to this equation is this kind of exponent. Okay, so you can either just focus on the idea of generator or on idea of Schrödinger equation. And maybe it's a matter of preference, but I prefer this kind of approach, where you think about generators rather than Schrödinger equation, because this equation, it works for any psi. Okay, it's true for any psi here. So you can just rip it out and throw it away and just leave it as an equation for U itself. Okay, so it's Schrödinger equation is true. It's true for any psi s. Hence, you can have a dynamical equation for U itself. Okay, so it's the equation takes this form with initial condition that U at 0 is identity. Okay, so in this sense, you can kind of forget about state and focus on the thing that governs the dynamics in your system. As a matter of fact, this is my preferred way of thinking about it, because it's very tempting to say that, okay, my system, I identify my system with its state. Okay, so I say, when I think about state, I think about this psi, all right? However, this is, psi changes in time, right? So does it mean that when I have psi of t and psi of t prime, does it mean my system is different now because some time has passed, right? That would be silly. State is just some hat, the hat the system can wear, and it can change it whatever it wants. It just depends on some circumstances what the form of the state will be. But if you want to identify your system, what is its essence? What is its identity? I would say it's the evolution operator, or the Hamiltonian, the generator, right? This is what defines my my system, sorry. This is what characterizes my system. I just give you Hamiltonian, and now we know what we are talking about. The state is just let's say, a consequence of this dynamical law within my system. Okay, how states looks, this is just a consequence of that. So I prefer to think about U as a thing generated by H, in a pinch as a thing that satisfies this dynamical equation. And the Schrödinger equation is for it's just an extra bit. Okay, so Schrödinger equation, or dynamical equation we prefer, is one consequence. The second one would be a evolution operator, evo op satisfies something I call composition rule. Composition rule means that you take U of t and you take U of s, so we compose evolution operators, and as a result you get evolution operator of t plus s. Okay, and you can just show it algebraically. So you take this form, you take this series, write everything down, collect the terms, and try to gather them up in exp. Or you can actually use Schrödinger equation to find it in a more clever way, which I will do right now. So show it using Schrödinger equation. So if I set psi s equals u as acting on psi 0 as initial condition, for our Schrödinger equation, right? Then the solution of Schrödinger equation will give me psi t plus s that's equal u t psi s, right? This comes from yeah. So if I set this as initial condition, I solve my Schrödinger equation. This is a solution, and it's given in terms of evolution operator acting on the initial condition. But on the other hand, psi t plus s equals u t plus s of psi 0. This is also a solution, but for initial init condition, psi 0. Okay. And the two guys have to. It's the same solution. So ut plus s psi 0 must be equal to ut psi s, which is equal to ut us psi 0. Okay, and this works for any psi 0, hence we get our composition rule. So what this shows that the composition rule is actually equivalent to Schrödinger equation or to dynamical equation. Okay, so you can think of differential equation, or you can think of composing your operator, and to actually like to see why is it so. You can think because differential equation tells you what when you take a small change, right? So you take time and make a little step forward, and this is how you construct your derivative, right? And it tells you what changes. But now, if you have composition rule, I mean, you can compose operators, but you can equally well take an operator and split it into parts, right? So you could take your operator ut and just split it, for example, in like a million, like let's say, see, how they want to split it. If t is like n times some small delta t, okay, then you could split it into like delta t, right? Overall n times, right? So if you want to have so differential equation tells you about the small increments, right? But you can small increments can be achieved by just I mean, big increment is achieved by composing small increments, right? So you can go from one to the other through this kind of picture, right? We're splitting into small times. So basically, you can the properties of your operator that then are basically determined by this infinitesimal shift in time, right? Infinitesimal shift in time is nothing else than nothing else than a generator, right, of your unitary transformation, of your evolution operator, sorry. So there's intimate connection between composition rule and dynamical equations. And this is, like a basic stuff for quantum mechanics, but it's also like a basis for group theory, right? So this is like, there's some mathematical background to this as well. And, but the bottom line is that composition rule is it's not only like a very convenient way, a convenient property that you can use to like imagine that your evolution goes in steps of times, but it's also very fundamental stuff, right? A lot of properties essentially come from the fact that you have this composition rule. And if you lose composition rule, a lot of stuff stops to behave as you would expect it to behave. And I'm talking about this because we are in closed systems. The composition rules works, but the composition rule is one of the first things that goes away when you go to stochastic dynamics or even especially open systems, right? So have this composition rule in mind, and this is important stuff. And look when you lose it, okay? Because this will mean that you are in a new paradigm, essentially, okay? So finally, the third consequence, Evo operator, Evo op is unitary. It's unitary, which means that ut dagger equals ut to power reciprocal, how do you say it? U2 minus 1, okay? And it also equals to u to minus t. Okay, so it means that ut dagger ut equals ut dagger, right? And it's an identity. This is what unitarity means, and you can check this. So inverse, yes, thank you. This is what I want to say. This is an inverse operator, right? So it's like, this means that, I mean, this looks like evolution backwards in time, right? And it's like, we have, for positive times, you can think of evolution forwards in time, but you can go back, right? You are not, it's like, you have this symmetry in time in closed systems, okay? Because if you can go, you can go forward, you can always go back, and there's nothing. It's one-to-one. I mean, you don't lose any information along the way. Okay, you can always rewind everything easily. And to show that this is the case, well, you can do it from technical standpoint. If you take dagger of u and you just use your series representation, okay, you take dagger, and I remember Hamiltonian, the generator is Hermitian operator, so it's immune to daggers. You can stab it with a dagger and it just doesn't care. The only thing that's not immune is imaginary unit. So taking dagger, the only thing it changes, it just flips the sign. So rather than minus t minus it, you get plus it. Okay, which means that it's exponent of it h, which is nothing else than u of minus t. Okay, so this is straightforward. So the real thing is to show that this u of minus t is actually the inverse of ut, which you can use composition rule to show it quite easily. Right? You take ut u minus t. Well, composition rules tells us we just have to add. We just have to add the arguments. So it's just u of 0, and u of 0 is identity. Okay. And the same if you go the other way around. So u minus t with ut, it's also it's the same thing, symmetric. So is this a basic stuff for you guys? It's like you probably know it, and it's nothing new was said except maybe for my obsession with evolution operator over states. Okay, and it's one of those things that I'm really obsessed about, and I advertise it to everyone who will listen to me. So to get some hands-on stuff with this, we have a there is a assignment for you to consider. It's a very simple one. It just I give you Hamiltonian, which is for a two-level system. It's simple Pauli matrix, and I want you to use the definition 2, which is just this series formula here, okay? And to just calculate the exponent. And yeah, and have a look at that. It's something you can do analytically in this case, but word of caution, this is because Pauli matrices are very special. In 99.9999% of cases, you won't be able to calculate this exponent analytically. Okay, you will need some more refined, let's say, approach. But in case of Pauli matrices, two-level systems, this actually can be done completely. Okay. All right. So this was a warm-up, because now we get to more real thing, and maybe there would be something new for you here. So 1.2, maybe let's change the color. I like this one. So time-dependent Hamiltonians. And the dreaded time ordering operation. So have you heard about time ordering operator or operation? Oh, so you are like, you haven't seen the real horror yet. Okay, that's good. So you don't have any baggage with you. So everything you will see will be new, and you will become a master immediately rather than have to relearn stuff anew. So we talked about closed system that also isolated, which meant that Hamiltonian was constant because energy is constant if there are no inputs of no external fields that could just mess up with our energy. But of course, you can still have closed systems, so no other quantum systems around, but maybe there is some external field that pumps energy into our system. In that case, the Hamiltonian ceases to be a constant operator, starts to depend on time in some fashion. So system is no longer isolated, insulated, sorry, not isolated, insulated. Insulated, which means that you take Hamiltonian, take a derivative over time, and it's not zero. So it's some function of time, okay? Then you have in that case, your states will evolve. Look, even though I'm obsessed with evolution operators, I will still use Schrödinger equation when it's convenient. Okay, so don't judge me too harshly. So the Schrödinger equation in this case will be the form is the same as previously, but now this guy is time dependent. Okay, and what it means that our solution from before doesn't work anymore. Doesn't work anymore. Right? So you cannot the psi of t is no longer equal to e to I t, I don't know, h of t, question mark. So this kind of guy doesn't work, okay? This won't satisfy this Schrödinger equation, okay? Neither thing like e, I don't know, because maybe it's kind of weird. Why multiply by t if this also depends on t? So maybe you should write something like this, more fancy, right? So you just like maybe you accumulate the generator over time. This also doesn't work. That's also wrong. Okay, and maybe it's I have it as an assignment to check that they don't work, but maybe let's do it. Okay, because it's I think it will be instructive for you to actually see what are the difficulties here. Okay, why this nice exponent doesn't work anymore. So that's assignment 2. If you want to compare it with the notes as 2. So first, let's start with this guy. Let's show that this doesn't work. So all we have to do, we just have to calculate the derivative, right, of this guy, and show that it's not equal to right-hand side. Right? That's all you have to do to show that it doesn't work. And that's that's procedural stuff, some algebra, we can do it. So e to minus ith of t, which is exponent. This means that we have our so this e is just a shorthand for taking this series here. Et k factorial h of t to power k. All right. So we do derivative of sum. So we just enter under the sum and do the derivations. which, now we have, previously the time was only parameter, right? In the numerator, we didn't have to worry about operator, but now we still have parameter here, and we have a h that also depends on t. So derivative will hit both of them. Okay. So we can write it down as so first of all, the k equals 0 term, which is the first term in our series, is just identity. So the derivative just eats it. So the sum will begin from 1, go to infinity, and we will have two parts. One part is when the derivative hits the parameter in front. So we can write it as minus I minus it to the power k minus 1, and the factorial in the denominator will be reduced by one tick, right? Hope it's clear. If not, let me know. And in this pass, we don't touch the operators. And there is another. Right, because to power k, so the k goes in front, it's with the denominator. So the other guy, we don't touch the parameter, but we touch the operators. And you might be tempted here to say, oh, so this guy here, when I differentiate this product of operators, well, it's just k times h to the power k minus 1. Are you tempted to say this? Because you would be wrong here. Let's break this down. So what this means, it means that we have derivative, and we have here a product of operators, identical copies, that's for sure, but it's a product of operators, right? And there are k of them here, k times. Operators don't commute with each other. I mean, no, wrong. I said it wrong. The placement in the product matters. That's what I wanted to say here. Because now I have a derivative of product, so it's a sum of derivatives of each factor, right? But h commutes with itself. Okay, this is 0. Okay, of course. I mean, they're the same operator, but h with its derivative, this is not 0 in general. Sometimes it could be, but in general it's not. So what this guy turns into, this is a sum over j going from how do you say 1, let's say, yeah, from 1 to k, where you will have sorry about that. I don't know what will happen when I move it like that on the recording side. Let's move it here and hope for the best. Okay, let's note, don't avoid the corners. So we will have here a to the power j minus 1, probably j minus 1 derivative. And the rest. So k minus j plus 1, probably. Not even that. I have in my notes, this correction is not necessary. Probably. So this is a whole sum of weird stuff. Okay. So having said that, now we continue with our guy, and yeah. So this guy here, if I just shift the index k by one unit, I will get minus I h t, and it will reproduce the whole exponent. Okay. But so this looks promising, because this is like a the right hand side of the Schrodinger equation. That's cool. But there is this second part just trails after us. So from k1 to infinity, sum over j 1 to k minus itk k factorial, and we have this j minus 1 derivative. Okay, now I have to migrate this up. We remember about commutators, h of t, k minus j. Okay, so this is the reminder, and this is, it's not because of this guy, it's not h of t times e minus t h. Okay, so boom, Schrodinger equation is not satisfied by this form. Okay, so maybe it was too primitive. So maybe the other one is better. The other one was minus I, and we had integral here. Now, because it's weird, like it depends on time, and I just multiply by time. What's with that? It's just what's going on here. So maybe you have to integrate. But again, we take our sum minus a to power k factorial, and we have derivative of integral from 0 to t hs ds to the power k. Okay, and this is, qualitatively, it's the same problem as here, essentially, right? Just the derivative will simply eat the integral here, right? But still, what you will end up with, j1 to k minus ik. It's maybe a little bit less messy than previously. J minus 1, h of t, right? Because when I differentiate integral and the t is in the upper limit, I just throw away integral and set integrand at the time of the value of the limit, right? K minus j. And this is, it's not I h t, okay? E minus E. That's not it. So it also doesn't satisfy Schrodinger equation. So it was maybe not very difficult algebra, but it's a good a good lesson for future. If operators mind orders, main order of the operators are composed into. This is like the key to everything. Don't go into autopilot. Don't treat it like functions. It's really important that they don't commute. That's like, if they did, everything would be simple, but they don't, and that's why it's quantum. So what is the real solution then? Okay. The real solution to time dependent Schrödinger equation. So if I set initial condition as psi 0, okay, initial condition. Let me rephrase it. Limit initial condition psi t at t equals 0 equals psi 0. Okay, so this is a given, some given initial state ket. The solution is psi of t equals, how do I want to write it? Maybe I will write it like this. There will be an operator, evolution operator, acting on the initial state. Okay. But this operator will have like two arguments. It will tell us that it goes from 0 to t. Okay. Previously, we didn't have to bother about that because time was just a parameter. You could just add, I mean, take a difference of times that would give you like a propagation through interval and stuff like that. I didn't have to worry about it. But this one it depends on initial and final time, and its form drum roll. It has a series representation from 0 to infinity. There is minus I to power k. That's similar to previously, although there is no factorial. There's no factorial because we have something that I will call an ordered time integral. Okay, dsk 0 sk dsk minus 1, and you daisy chain it until you reach the say fat fingers, sorry. S3 ds2 0 s2 ds1. So you see, it's ordered because it's in this construction, in this thing, it's always like sk is the largest, s1 is the smallest. Okay, because s1 is only as big as s2, which is the next integral. S2 is only as big as S3, and so on and so forth, until you get to the last one, SK, which is, this is the T that actually bounds it from the top. This is an ordered time integration, okay? And this is my personal preference to go from K to 1 rather than from 1 to K. I'm used to that, and there are some practical considerations here.
K starts from 0. Shouldn't we do it like one more integral, like ds0?
You mean more than K integrals?
I mean, the last integral, like from 0 to S1, from ds0.
No.
Like it would be some from 0 to 1. There are two numbers, so there would be also in integral for S0.
No, there are k integrals. So we go from S1 to Sk, that's k, okay? And they are ordered. So the last one is bounded from the top by the next to the last one. So in case of two, maybe, right? If you have only two, then you would have 0t. I'm probably not understanding the question, but for two, you would get S2 ds1, okay? And the
That is my question, because in the sum there is also
k0. Okay, good, very good. That's why in the notes I'm using the, yeah, okay. This is like a shorthand, let's say, because it really doesn't make sense. So let's write it like this, because k0 is just 1, okay? Because like no integrals at all, okay? So that's the shorthand. I sometimes might start to use it from time to time. Sorry about that, but in the notes I'm taking care to keep it like that. So I will keep it here as well. So this is ordered integrals, and the order matters because it defines the order of generators in the sequence. Okay. So we have a h of S1 is on the very right. Then you have h of S2, h of S3, and so on until you get to the last one. So this is okay. So we can, to verify that it is actually a good solution. I have it as an assignment, but again, we can do it because it's a straightforward calculation. So we can verify that this is a good solution by, again, doing the derivative. So let's take a look here. So if I attack this with derivative, right? T. The first guy goes away as usual. That's good. So this is the only thing we have to worry about. The only place that depends on t is this last integral, right? The last guy. So it's very easy to calculate the derivative. You just consume this integral and set the last guy sk to h of t and sk here to t, right? So you do the derivative, k1 to infinity minus I k ht. Let me write it like this: 0t s k minus 1, 0 s2 ds1. We have the rest of the guys. Okay. So I can pull out. So basically, I can pull out IH of t from this series, right? So the k equals 1 term will give me identity. So this identity, essentially, right? And the rest, I just shift the index 1 unit forward, and I will just let's say k prime from 1 to infinity, -1, k prime, t ds k prime, 0 s 2, so s1, s k prime, h s1, which is just, we reproduced the series again, which means it's minus I h t u t0, okay? Which means this form satisfies the dynamical equation, therefore it satisfies the Schrödinger equation. So the key to satisfy Schrödinger equation, dynamical equation, is to have this, the evolution operator has to have this kind of fractal form, right? That you can, like, when you calculate the derivative, it will, like, the thing, it will spawn a thing that you can snap off, and the rest will just reproduce itself again, right? Exponent has this property. That's why it's so popular in exponents are everywhere, because they have this kind of fractal form. A derivative for exponents is just exponent again. And but when the generator is time dependent, it's this kind of series that kind of behave like exponent in this sense that it has this fractal structure. And this is the reason why this series is conventionally denoted as time-ordered exponent. So ut0, conventionally, people, which is, again, this is this fundamentally, this is it's defined by this series, time-ordered integrations. It's to hsk hs1. People denote it as t time ordering, e minus I 0 t hs ds. So this is time ordered x. Sorry. So at this stage, you can just treat it as a big fancy symbol, okay? TE to blah, 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 all this stuff. It just means it's an alias for this series. The series is the thing that we can actually work with. But this is this fancy symbol. But why call it exp? So I want to try to, like, motivate why this notation actually exists here. And the motivation is, let's look at the normal exponent of a normal function, okay? Let's play with ordering integrals, but with standard numbers. So consider, maybe you guys want a couple minutes of break or something? No? It's okay? Good. Or maybe a couple minutes, we can always do that. Okay, no break, too late. Let's continue. I will, maybe I will finish at the end or something instead of doing the break. Okay, so consider a exponent minus I, you get integral a1 0 t. Before that, one quiz question for you. Imagine if we had our Schrödinger equation, we have a Schrödinger equation, this guy, we want to solve it, but we set a initial condition. What if at some t equals s greater than 0? So basically don't start from 0, but from some other time. So that we are looking for solution that would be UTS. Okay, that would be our solution. How would it look like if you would have to guess? How would you modify this?
For the right? Or not? No. I don't think it's right.
Just guess. Don't think about it. Just intuitively. What would you expect?
Cut some integrals inside.
Cut integrals. Interesting.
Get rid of.
There is this number of bank, wouldn't it still end up exactly the same?
And what would you say if I proposed that if I have this lower that this is the lower limit is what corresponds to the initial time? Would you agree to that? So in other words, what I'm trying to sell to you, if I did it like this, all you have to do actually. Okay. You can check that this satisfies the Schrödinger equation with the initial condition given here. Okay. You can check composition rule, but that's assignment for home assignment. Okay. Composition rule also works. Or actually, we'll talk about that. But so this is like the modification you have to do. Okay. If your initial condition is not at 0. And this is enough. Still ordered, but they just start from different flow, different initial time. And hence, if I do it like this, S, the symbol reflects this by, so I have to change here, U, du, okay? Right, so it's intuitive. The notation tries to be intuitive in this sense, okay? All right, so having said that, I have some assignments for you. This was tracked. No, we can continue with a why this series should be thought of as some kind of x, modified x, but still x. What's the why? I mean,
What is the property when multiply it by t?
It's at the moment treat it just one big symbol.
Okay.
Okay. The next step will be to actually treat it as some operation that acts, but that's next step. Okay. For now, you can treat it as, and this is the safest way, by the way. The series, you can always work with it. You can do algebra on it and stuff like that. It's under control. So this is like your fallback scenario always. And this for now, just a big fancy symbol.
Series that works like Taylor series, but in complex numbers, and I'm not sure if those are
Lawrence?
yeah, I think it was
Okay, you know what, guys, you're asking for it, so I will tell you. I will just skip to the point. Okay.
Because maybe it's like the multiplication operator we are putting here because previously it was more trivial the solution, and now we will get that the operator is more non-trivial solution, like more general, right?
So what these things like insinuates, okay, what this notation insinuates, that T, you can, it's valid to think of it as a linear operator or operation that acts on products of time or parameter dependent operators. Okay, and when you treat it like that, then you can actually think of this as T acting on exponent here, with exponent defined as a, this the same way we did previously. So in that case, if you think of T as an operation, then you would TE minus I S T H U supposed to be a next point in my program, but you asked for it, so you would you treat it as a linear operation, okay? So you just expand your exponent like a normal exponent, non-fancy exponent. Power k, all right? And then T is linear, so you can write it as k. Let's write integrals. Let's enumerate integrals in some way. So uk to u1. So we have k times integration, but it's not ordered yet. Okay, it's just independent integration variables. Each goes from S to T. And T acts then on the product. UK, U1. And now to resolve this mysterious inscription, you have to have some rules. Okay, what T does to, what T is supposed to do to a product of parameter dependent operators. And it's in words, because you defined it in words, it's the best thing, the best way I can think of. Yeah, so here. So how does T work? T. So let me just dictate this. Where is it? Return the products. So it acts on products. This is the only things it will act on. Okay, at least, yeah, it's the only context where T is used is when it will act on some products. Okay, so the only thing you have to know how it resolves products. So it returns the product. So we know we get our product back, but rearrange operators. Rearrange operators. HUI from left to right, or from left to right, right? In the descending order, descending order of the value of their arguments. Their arguments. It is a mouthful. Let's simple example. So if you take example, if you take t parameter t that is greater than s, okay, and you have to resolve a product of two operators, say s t. So what it tells us that you return the product again, so we will have h, but rearrange them so that the largest value of the argument is the leftmost and the smallest value is the rightmost. So it ts, okay?
But same will be with the minus values, like everything.
Oh, this is extra thing.
Okay.
This is extra thing from field theory where you have fermionic operators and stuff like that. But this is when you talk about standard dynamics with time-dependent Hamiltonians, don't worry about signs, just this rearrangement. But you heard right. There are versions of ordering that actually do some shenanigans with sign as well. But this would be a field theory, not this non-relativistic quantum mechanics. And if you have a product that's already ordered, just right, you just don't do anything. All right, this is the recipe. And why it works, why it would work for, so here, this is the solid foundation, right? This is the solution to equation. This is the thing that's real. This thing is some mumbo jumbo, right? And it's supposed to be, after we do this, after we resolve this guy here, it's supposed to give us this, right? So how is it possible? So first thing first, if we want to resolve this t here in each term, we have to know the which parameter, which u's are bigger than the others, right? We have to have some definite ordering of those integration variables. Without them, we cannot resolve anything because it's unspecified. So here, you just don't know what to do. Okay, you have to do something extra to actually arrive at to transform it in such a way that in the end you can apply this simple rule. Okay. So in other words, we have to take those unordered integrals. So the first thing we have to do, we have to take those unordered integrals and turn them into ordered integrals. Okay. And so I wanted to talk about it first before we get to here, but you asked. So now we have to go back and talk about ordering variables in multiple integrations. Okay, this all are technical stuff, but if it would possible for you to remember all the tricks I will show you soon, you will be like a real master of evolution in quantum mechanics. But if you don't remember all of them, at least remember where you can find them, okay, in those nodes. And then whenever time ordering is one of those things that I feel it is kind of important, as we will see. I mean, most of this course will be about, there will be some time-ordered exps everywhere, okay? So it's very important stuff. In field theory, you already noticed there are also some kind of orderings, some variation of orderings, but this is very important, but it's also one of those things that's very poorly taught in general. I mean, I did not understand time ordering until I just sat down to write those notes to prepare first edition of this lecture. I actually spent a couple of weeks reinventing the ordering. Okay, so if the only thing you will learn from this course that will stay with you, if it will be about time ordering, I will die happy. Okay, because this is like, if this will be the thing you will learn, I'm mission completed. Okay, it will be, or at least you will remember where to find the some formulas that can be used afterwards. So this is like this is a real shit. Okay, real thing here. It's not really about open system and stuff like that. It's general stuff. Okay, so after this hype, now I have to deliver somehow. Okay, but yeah. So let me try to explain. So if you go for, I mean, first thing first, time ordering, you can live without it. Okay, this is just convenience, notational. You can always think about it as a notational convention. Okay, because underneath it's always this thing. So any properties, anything you need can be always derived through procedural algebra on this kind of series, okay? So this is extra. So at the very least, you can just forget about, I mean, if you want to be safe, you can always work on the series, which is robust, nothing surprising there. So this is like extra bit. Now, if you, in spite of that, still want to learn a bit about this trick, this ordering operation, there are things to remember. One, this T, it looks like an operation, like an operator, which you might think it's just a universal thing. I can just take it, apply it in some completely different context. No, treat it as thing that only acts on this specific exponent, okay? So the only thing it has to be defined on is how to resolve this product, okay? If you have some H, T, and some, I don't know, A, S, something like that, you might wonder, okay, how to resolve this then? It's not defined for this. It's not defined because you will never have to resolve this kind of product. Okay, if you have to, you messed up. Okay, something is wrong. So it's an operator, but it's very specific domain. Okay, for everything else, you don't have to think about what it does, right? So that this is like a second thing. Third thing, for example, what we have here. I already alluded to that. You would like to resolve this T acting on this guy, but the recipe is to, the recipe requires you to know what is the descending order of arguments actually, right? In this case, it's undefined, which means there is no way to resolve this T at this point, okay? So bear this in mind. T on its own basically doesn't do any work for you. You have to work around it to do and the T is the last the most smooth-brained step you have to take. Okay, there's nothing mysterious about it at this point, but you have to prepare everything around it. All right. And again, you can always fall back to this solid thing and check your calculations, check your tricks that you just deployed with your understanding of T. All right. So all those disclaimers aside, so to actually resolve this guy, we have to define some order for those integrals. Unordered integrals have to be changed into ordered integrals in some way. And there's a procedure for doing that, okay, which I will try to explain here, okay? And there are some tricks here that are worth to remember. So to talk about those tricks, let me talk about exponent. Consider, so we have exponent minus I integral st, but rather than operators or time ordered operators, just let's grab some generic C number function, just a number, which you can, do whatever you want. This guy is, of course, this is exponent, nothing fancy here, standard series. Oh, no, don't do the thing. 1 plus k1 to infinity. So minus I k factorial, and st f u, sorry, I didn't mean to insult you, and to the power k, okay, just standard thing, which then we can plus do a similar thing we did here. So let's label our variables for bookkeeping. St duk du1 fuk fu1. And of course, the order of f's doesn't matter because they are numbers. You can always rearrange them as you please. They are not operators, so you can do whatever you want. Now, so again, we have here a k times integration, but variables are independent, are unordered. So this kind of unordered set of k variables, there are as many ways to order it as there are permutations of k of set of k indices. Okay, so as many ways to order this guy as there are permutations of set of indices, okay, which is k factorial, okay. There are k factorial ways to order set of k variables. K factorial, which you can like, it's kind of like, ooh, does it have something to do with this k factorial here? Yes, it does. Okay, yes, it does. So this is no accident. So, for example, what I mean by ordering, okay? So let's take the simplest case of two variables, du2, du1. What I mean by defining order for them. So I can write here 1, just 1. It's no big. but 1 also equals this Heaviside theta. You know what Heaviside step function is? Right, so this is step function. Step function. So theta of x is 1 when x is greater than 0 and 0 otherwise. Okay? So here we have theta that gives you 1 when u2 is bigger than u1. And this one is the other condition, when u1 is bigger than u2. So they are, whatever the order between u1 and u2 is, one of the thetas will activate. So you can split 1 into this kind of combination of thetas, right, for free, right? Yes.
Where they are
Equal,
but this is integral, so it doesn't.
exactly. Theta is not defined when at 0 exactly, so when u1 is equals u2, but we don't have to worry because this is a measure 0 set, so under integrals it's just immaterial. That's why it's a good trick when you have integrals. Thetas otherwise are that's a monstrous thing. But we can consume those thetas with our integrations. So the first one tells us that everything goes to 0 when u1 is bigger than u2. So it translates into u2 can be whatever, but u1 cannot be bigger than u2. So you can take care of it by defining your integral limits of your integral. Okay, so this takes care of this guy. So the other guy, analogous way, du1 as u1 du2. Okay? Make sense? We got 2 ordered integrations now. And there are 2 equals 2 factorial. That's the number of permutations, right? So the assignment that I propose to you, it's assignment 4 to get acquaintance with this kind of tricks. Assignment 4 is to find orderings for triple integral. Okay. Essentially, you are using. I advocate always for using a trick with thetas, but there are some genius people who can actually draw the answer. They just draw it on blackboard. They have some triangles. I never understand how they do it, but some people can do it without thetas. They just with some pictures, and I never understood how they do it, but they are some geniuses. They can do it. I prefer this procedural approach with thetas, and it can be iterated for any number of variables. It's labor rows, of course, but it gives you the result. Assignment 4, you check the solution. There is a everything's written down. You can also try to. Yeah, I kicked the cable. Sorry. Hopefully the recording didn't break. Should work. Okay. Yeah, it shouldn't have problems. It's true. All right. So, so in general, when you do these orderings, what you are getting, so for this k variable integration, when you go through all the motions, you will essentially get a sum of ordered integrations where you have all the possible permutations. It's just realized with all the possible permutations, which you can write. We almost finished.
It's like getting some characteristic functions on some spaces right now, because we got this Heaviside function, and now we should take some when going into higher U in K, getting some characteristic functions in there as well.
Well, you could do that, but it's the thing I understand. You just stick to one integral at the time, and you just go this bisection, but for every for every case. So it just splits into decision tree that's bigger and bigger and bigger and bigger. It's laborious as hell, but some people can just imagine characteristic function, so can draw it and figure out the answer. It just beyond me. Okay, I just prefer thetas. But what if you have some ideas? I mean, more power to you. But there is one low IQ approach that works for everyone. Okay, it's a lot of work, but it leaves you with the result. So, if we define, we're almost done. One last inscription, and we wrap up. So if I define this is a set of all permutations. Permutations of k indices. So I can, if I take this unordered integral U1 st, and here I have my f uk f u1. So this I can turn into sum over permutation sigma from our set, where we have st d q sigma k s u sigma 2 EU sigma 1 and the functions UI. Okay, so what does it mean? So sigma, capital sigma is set of all permutations, and permutation small sigma is a mapping, right? It maps one set of indices to some other set of indices in a one-to-one fashion, right? So for example, the simplest one would be if it took our original ordering and just reversed everything. That would be one of the permutations, right? And in that case, so you get k minus 1, blah, 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 to 1, and reverse the order. So in that case, you would write sigma of k, that would be 1, okay? Sigma k minus 1, that would be 2, and so on. But it's one-to-one mapping, so inverse map also exists. So inverse map here would be sigma minus 1 of 1 would be k. Sigma minus 1 of 2 would be k minus 1, and so on. Okay? So you have sum over all the permutations, and you have ordered integrals, and which variables are first, which are last. This all, all possibilities, essentially. But now, you see, sigmas 1 to 1, so sigma to minus 1 always exists. So now I can change the names of my variables, integration variables. All right. The latest always call it UK. The last call always call U1. In that case, I can have my DUK as U2 DU1. Okay. But permutations are not gone. Sigma. The permutations now appear there have been shifted to our function here. Okay. We changed the names of variables so that we could just get one standard integration of that integration, but the price we pay, we have to, you know, compensate it for in the arguments of our functions. So we have sum over the permutation of this product, but you know, this is a product of numbers. So I can take any of them and rearrange them so that UK is always the last, U1 is always, I mean, UK is always the first, U1 is always the last. That's because they are numbers. And there is always U of every index that I require, right? Because sigma permutations are one-to-one maps. So I can write it as DUK as U2 DU1 and UK FU1. I can also rearrange, and I'm left with sum over sigmas that actually don't do anything anymore. And how many permutations are there? K factorial. So this guy is K factorial. Okay. And this K factorial will nicely cancel with this K factorial here. So in other words, if we go back to original dilemma, theta infinity, K factorial cancels, so we just have a minus I to power K. We have ordered U1, and we have ordered F1, okay? In other words, because F is number, it commutes with itself, I can freely switch between like unordered exp and ordered exp, because you know this is still the same exp, but it's given by our ordered formula, right? So that's why you know we have TE still. You symbolize it as some kind of exponent, because it's if these operators commuted with each other, it will just, you could freely transform one into the other, right? So this is what you can do when your integrands are commuting with itself. So now we can jump back to here, okay? And so what we have to do now, we have to do the same trick to order our integral here, okay? And we will get K0 infinity minus IK ST DUK DSU2 DU1, okay? We'll have our sum over permutations T HU sigma K sigma 1. Okay, this is what it turns into. But here is the thing. Because there is this time ordering around this product, you can, the actual order under order of operators doesn't matter, because T in the end will fix it to something, right? It will always make it right. So this is like the rule of thumb. When you have t, you can just treat operators as numbers. So you can rearrange them freely, okay? Because whatever you do with them, in the end, once t is resolved, it will do the thing, it will fix the things that you did to them, okay? So that's why you can do the same trick as with functions f, and you just consume the permutations. You get your k factorial cancels with this one, and then you end up with t acting on the product where the variables now have definite order, which means you can resolve them. You can resolve t, which then lead us to this form, okay? So I think this is a good place to stop. Hopefully it wasn't too boring talking about this stuff. Let me see. Do I have a assignment for you? You know what? No, I do have assignment for you. One thing to calculate a bit. You know what? Yeah, one more. So we jumped a little bit around the notes. So consider assignment 5, okay, which basically to check that if you use time-ordered exponent, but the Hamiltonian is actually constant, you will recover the standard exponent without time ordering. So time ordering is only necessary when it's necessary, in other words, okay? And to also check that if your time dependence is just by multiplying by a function. So it's not really, you still have, everything commutes still, okay? That's also, you recover the intuitive exponent. Just check it out. The rest this will do next week.